Donc, nous commençons et je passe la parole d'abord à Carlo Rubbia qui va nous expliquer qu'il faut transporter l'électricité de l'endroit où elle est produite à l'endroit où les gens vivent. Et donc, Carlo, je te passe la parole.
Okay, fine. So here we are. I can see a very bright audience building up here. It's okay. Anyway, so I will make half an hour of a presentation, and then you will have your discussion with the board. So it will be an introduction to the problem. This thing doesn't work. Where is it? Here. Okay. Now there are two papers which I would suggest in order to get more information on this. One of them is a paper which we put together for the developing of MG2 table. And the second one is a paper in which we worry about AC current versus DC current, which is another very important question which we are discussing, because obviously if DC is the way in which you're going to produce this current, AC may not be completely negligible as an issue. Okay, so let me start at the beginning with some general considerations about energy-related new technology. And I think that this is the only key to success. Let me explain you. The current worldwide energy supplies is based mainly on the availability of fossil fuel. And they remain indispensable to the decade to come. People would think that fossils are over and finished. I think they're really talking moonshine at the present stage. The transformation to energies with lower emission and a quantitatively significant management of the CO2 are amongst the most important technological challenges of our time. We want to get to fossils with no CO2 if possible, and as a subject on which, by the way, I may be able to discuss if somebody wants some answers to the questions. But this is not the subject today. In order to curb environmental changes, it is necessary to proceed simultaneously on two parallel lines: a more efficient and friendly utilization of fossil fuels, curbing the effects of the anthropogenic emission, and two, the development and progressive utilization of the renewable energy sources. Both novel methods of energy productions are presumably the only practical way out of the anthropogenic warming threat. All people which propose to make other phenomena in which you can survive with the CO2 emissions, adding, for instance, SO2 in the atmospheres. So geoengineering statements are so far failed, including also the one of putting huge amount of CO2 inside the underground boxes and so forth and so on. So essentially, it's quite clear these are two things which are, to us, more efficient utilization of fossil fuels and development of. Now, first in question important is parity to innovations to renewable energy, which is, of course, is an important condition. So you can see from here that indeed all the made productions of renewable energies, which are indicated here, which are obviously solar, wind, and biomass, are now, over the relatively short period of time, dropping the cost to the general level here of the wholesale parity value, which is somewhere between $50 and $80 per megawatt hour, which is the one corresponding to the majority of fossils. And therefore, the parity of fossils will be reached in a relatively short time. The most important effect is the drop in the solar PV from today to 2020, and also the activity of several biomass solutions, which are becoming perfectly interesting values. Now, the contributions to the various forms of renewable energies are indicated here. We have essentially here a number of alternatives. We have typical yield of this material are indicated there for biomass, which is about 1 gigawatt electric per square kilometer per year. You can see here the colored the lines where, in fact, most of the biomass exists. This is green biomass. We have here the geothermal solution with the geothermal energies. Let me remind you, very strong geothermal in Italy, big stronger here in this region. Turkey is also a very important place for geothermal, and a few other places are available in which geothermal energy could be made available, which is 1 gigawatt again electric per square kilometer per year. This is wind. Wind is dominated to the periphery of Europe. The central part of Europe is essentially windless, but there are areas somewhere here, and mostly the North Sea, where there is a huge amount of of wind availability. And hydropower, of course, is indicated where the mountains are, the Alps and the other chains which can do that. These are the Evanto power which you consider to be available within Europe as a whole for the various channels of renewable energy. This is a theoretically maximum, what's going on, available level. Now, of course, a most important winning element here is solar, which, as you can see here, is by far the most important solution. You can see, this machine is terrible, which represents here essentially a consumption which is 250 gigawatts electric per square kilometer per year. And in fact, this has to be compared. What are the numbers for Europe? You can see here that the Europe plus desert in 2050 will require 7,500 in those units, and worldwide will be 3,500. So you can see that clearly solar, it's an absolute necessity in order to get a substantial development of renewable energies available in the system. Now, the next question here, of course, is the amount of size of this phenomenon. You can see here the area required to supply the world by 2050, Europe, etc. And you can see that a place, for instance, a small little area like the Nasser Lake area in here could contain enough solar energy to satisfy all the requirements by the year 2050. So it's a fantastically large resource which could be made of some use. But, of course, the trouble is that it's very far from where we are. Now, let me quickly cover the various solutions. Let me, first of all, touch the question in wind. You can see here from this graph here that the wind is essentially dominated here in, let me go on with this. Let me go forward, further on with this. Now, this is a terrible machinery. This is essentially, you can see here, the wind is, the power of the wind in Europe is indicated there. You can see that the wind is essentially, goes like a cube, or the speed. You can see where the big wind action is. Most of the offshore is there with a little piece of Germany in there. And there is another region here down south of France, and the next area is Greece. And everything else here is windless as far as we are concerned. The other important question is dimensions. This is 1,000 kilometers distance between, for instance, to go from where the wind is down to where you are. It takes easily thousands of kilometers distance, and so forth, the numbers. Now, let me continue with this thing. Now, this is the numbers where they come from. A fair share of this wind capacity will be growing offshore for several reasons. High resource level, lack of promising sites offshore, and growing public opposition against future onshore wind parks. Now, and that is the key to the argument which we are here discussing. Transmission line will need major innovations in order to keep costs to a manageable level. This is what we are going to be discussing later on. Now, just to give you some more illustration about the wind, this is for instance, how serious the wind variability is. This is worth remembering here that the percentage of electric demand delivered in all the wind turbines during the year 2007. Now, average over the year, the wind power delivered is only 18% of the installed capacity. You can see that because you never get the energy when you want it, but it is available. And you can see from here that the extreme local variability of the wind resources require vastly interconnected electric system in order to eliminate blackouts. That's another way in which wind will be acceptable to the system in questions. Now, this has produced a very major evolution in the German system. I'm using the German system as a reference case. This is the present situation of the general electricity transmission within Germany. You can see here a number of possible solutions. You can see where the areas of major activity is. Here, coal and formerly nuclear and so forth have produced sources which are relatively near to the place where the energy is required. But now, this is a terrible thing. But now, in 20 years from now, the situation will have to be completely different. You can see here from this graph that, in fact, there are lines which are now being planted and proposed for the future. This is reality. And here's a 12 gigawatt line, for instance, going from the Northern Sea down to the bottom of near Munich. You can see another line of 6 gigawatts, another line of 6 gigawatt here, another 4 gigawatt there. But by 2020 and beyond would be necessary in order to establish the connection between where the renewable sources are and where the electricity is needed. And this is the kind of dimensions. You can see that this is essentially all several hundred kilometers in distance. Wind expansions therefore require high power lines larger than 700 kilometers. Now, the other important question is it's essentially concentrating solar power. Here's a famous picture from a Spanish solar power plant with mirrors. Actually, there are two possible alternatives which we are now presently working on and discussing. One, the top one is a so-called Fresnel concentrated solar thermal collectors, in which the light is collected essentially by mirrors with Fresnel vectors, and then there is one receiver tube at top. And the second one is the one of the solar thermal collector here, which is well known, as you well know, but this is a representing system with the tubes in here which collecting the light in the receiver system. These two systems now are both developed. It turns out that developed, especially in Africa, indicates that there are lots of extra problems against the parabolic trough, and in fact, the linear Fresnel concentrated solar thermal collector is gaining a lot of momentum, and that probably will be the solution to the future. So, before I get further, I'd like to therefore make a conclusions. What are the key problems of renewable energies? Now, one should never forget that the best energy is always the cheapest energy. The cost of renewables must be strongly reduced in order to ensure cost competitivity with fossil and nuclear, and this is exactly what I would say you in transparency before, that by 2020, we'd expect that all the basic, most important renewable will win the fight in getting an economical solution to the energy. Now, the next problem is the one which I mentioned before for giving the example of the German wind. Energy must be available when it is needed. The variability of solar wind must be curbed with the help of energy storage or other methods like that. There is no known efficient way to do the energy storage with wind. There is energy storage possible solar. You can keep the warm, hot liquid from the sun or gas from the sun for overnight, they recover it, but it's still a technology which has all to be developed. And apparently, without energy storage, it will be very difficult to get this business going. Now, the other important question, which I think should be kept in mind, is renewable energies are mostly generate electricity when compared to fossils which produce thermal heat. Wind, solar, geothermal, they all produce electricity. Biomass, they all produce electricity in one way or the other. Therefore, we are changing the nature of the transmission instrument. Now, there is an important difference between total energy per person, which should be reduced, of course, and the electricity per person, which will be increasing. There will be more and more, because of the transformation, more and more money will go into electricity, and therefore less money will go into other systems if you assume that you also to be saving energy, especially true for Europe. Renewable energy, on the other hand, require much wider surface of collection, locating specific locations in which production is optimal. I gave you the example of the wind. I gave you the example of the solar. Not everywhere you can do this system. And normally you can do these systems only where there is no people. So the distance between where the use is and where the source are necessarily separated. It's not the case for coal. You can put coal anywhere you want. It's not a problem of nuclear. You can build a nuclear station where you like. But it's certainly true for wind. It's certainly true for solar and so forth and so on. Electricity at very high powers, as I saw the example of the German situation where you have power up to 12 gigawatts, must be transported and over a much longer distances than today. They have to be comparable with one possible today for natural gas and oil. Let me tell you, the longest natural gas pipeline between China and Russia is 5,200 miles, almost 8,000 kilometers, with a tube to transporting energy. There is no 8,000 kilometers cable for electricity. But if electricity is going to be the winning horse, then you may need also something similar in that particular frame of affairs. Now, this is the summary of what I said to you. This is coming from a diagram from Eumena. You can see that where really we have to go and how important it is to find a longer distance, which is between electricity. This is, for instance, it is geothermal. It may come down to this. This is you can see there, this is geothermal in various places. Then you have solar, also concentrating solar all over. In here, you can see that how much is being developed in that area, including this area here. Then you see hydro. Again, is this drawing here. You can see hydro sitting here and there, over there. You have biomass, which is also indicated all over the places. And they all have the characteristic. This is about 2,000 kilometers from here to there. So this is 1,000 kilometers, the distance between here and here. So you can see that distances are becoming extremely important. And if you want to carry out this kind of sources of various kind of renewable energy with electricity, you may need to have structures which have the dimensions which is shown in here. High power lines may lengths of more than 4,000 kilometers. Now, the next question is the purpose of our presentation today is long-distance electricity transport with superconductivity necessity. In general, it's been so far preferable to produce electricity locally with transported fossils, nuclear or otherwise, but optimally produce renewable energies, wind, solar, and hydro, generally located away from densely populated areas. Transporting long distance large amount of energy with electric grid is becoming a critical issue. Present methods being concentrated either with aerial lines at the highest voltage or ordinary underground underwater cable operated somewhat lower voltages. So far, conventional superconducting lines have not delivered competitive alternative, since one, conventional niobium titanium cables at somewhere between 1.6 and 1.6 and 4.2 Kelvin are cryogenically too complex, and the new warm superconductor material like liquid nitrogen temperature are too expensive and too delicate to be constructed on a very large size. We are not for tomorrow to have a long cable carried superconducting at the liquid nitrogen temperature with this kind of material. It's built as, now the point which is the purpose of today's discussion, and it is a simple new compound, the magnesium diboride, has appeared to us as a new solution which may provide low-cost superconducting cables sufficiently high cryogenic temperatures. Okay, so let me continue with this. Go to the next step. New choice of magnesium diboride. Now, the superconductivity was announced only in 2002. A new compound, magnesium diboride, was acceptable. Magnesium diboride is still under development. Here, Mr. Grasso, which is the chief of commander of the Columbus company. And you can see what the characteristic of that is, which is mentioned already by Klapisch before. The temperature is, the critical temperature is about here, you can see it's 39 Kelvin. And the manufacturing of wires is simple, in situ powder with a method which will be described in more detail, I suppose, by Columbus company. There is a chemical phase in which boron and magnesium, which are both elements very abundantly available worldwide, are putting a reaction in 900 degrees in argon, and you produce out of that magnesium diboride. Magnesium diboride then is transformed into a metallurgical phase in which you make a tube filling, wire drawings, and coil rolling. At the end, you get a wire which is coming out with a long length, a possibility of this extremely simple method of producing cheap chemicals and drawing the wire. It is very analog to the niobium titanium, which has been the victory of the niobium. In fact, you can make easy wires. Wire unit length up to 4 kilometers in a single piece, easily scalable. I think that Grasso will tell us about how the numbers will come on. It will be 20 kilometers by increasing the build size. So in one line, we can be 20 kilometers, one single wire every 20 kilometers. You got to have a splicer which join the various lines out of the system. Okay, fine. Now here there's one more point I'd like to cover, is the question of DC versus AC operation. Personally, I do not believe the AC power transmission system is to be out. And you can see from the graph in here to the left and right-hand side, the cable peak current for this cable is 5,000 amps. For DC, this is the critical value. You can see as a function of the cable current, the cable peak losses in watts per square meter for a variety of choices of materials. And you see it is quite clear that the amount of power which is being dissipated because of power losses is very fastly changing with the current. This is an order of magnitude between here and there, and this is occurring with the cable peak changes a few times. And therefore, if you can choose, it should be possible in terms of, although it is prudent to concentrate to DC power system, no doubt also AC system will have to be considered. Let me give you as an element for the story here, 1 watt per meter level coming from warming losses is indicated from this point. You can see that if you reduce the 5,000 amps of critical current to something like 1,500 amps or so, in fact, you will be able to run an AC line
in a sensible way with a fraction of watt dissipated per meter, means a kilowatt per kilometer. A megawatt for 1,000 kilometers compared to the gigawatts you carry is certainly an interesting number. Okay, now there are lots of practical cable, no question, Grasso will talk about it, which I indicated here, which have been working, and there is one important step which was done recently, which is a work done by CERN and IASS, which we have done together, and essentially a new solution because it's more abundant, critical temperature, readily manufactured wires, wire length of 20 kilometers, etc. Now, a joint CERN project worldwide for its achievement has been a tremendous success. In fact, in October 2013, we succeeded in taking a 6 millimeter cable with 2,020 meters has been produced, and this run at 20 Kelvin at something like 5,000 amps. In February 2014, it set to 6 cables, with a total 18 millimeter diameter being reached at 20,000 amps at 20 Kelvin. This 1.6 diameter cable operated at a very modest voltage of plus or minus 120 kilovolts, and therefore 5 gigawatts of electric power, which is the power of the big animals that the Germans are building to cross their country, will supply, for instance, 2,500 windmills of 2 megawatts of power, or about 10% of the whole electricity of France, and this is operated on a cable which is the diameter of my finger. So it's a remarkable result, which it seems to me should be looked into its significance, and it is, in fact, it's not producing any heat because there is no Ohm law. But anyway, there's the kind of thing. Now they show you very briefly how the tech looks like. This is the CERN station, which has been drawn in here. Here is some of the parts of the station, which you can see how big it is. That line you see on top here is representing the distance of 20 meters from back and forth in here. This is the dimension of the coil needed to carry 20,000 amps through the system, and this is the cryogenic system behind. And this is a proven capability. This shows more clearly how the system is put together. The cables which have been used are to the left, the 6 millimeter cable, to the right, the 18 millimeter cable that have been successful, and so forth and so on. And 10 gigawatt will require 250 kilowatts, and so forth. With that, or you can put more cable and go down with the voltage if you wish. Okay, now let me try to conclude this story in the next 10 minutes, saying essentially a detailed engineering design is now needed. A number of superconducting AC, DC alternatives, all based on magnesium diboride and temperature of the region, must be better clarified. Now, one question is, AC conductors, you need in the pair for DC, you need 3 lines for AC. Are they in the same conductor or they're separate? That's the question which you have to decide. Cooling can be either liquid hydrogen, as you'll see, or helium gas followed by liquid nitrogen at 65 Kelvin. Single gas helium to room temperature is too demanding. Next, optimum distance between the cryostation. How far do you want to go between you have to put a liquefier to start again? We are talking about a few hundred kilometers as a distance between the various stations, but this is something which has to be discussed. Then the other important question, this thing will travel mountains, will go in under the water. So what is the largest vertical difference allowed in each segment? Now, the other question is, almost inevitably, to go from Europe to Africa, for instance, you need underwater operation. Are you going to get underwater operation of superconducting? If so, at which depth and which distance? The other question then is insulation. Since the voltage used for this system is substantially less than the voltage you can obtain with with an ordinary cable, and in fact the current is very cheap because this diameter carries 20,000 amps, so if you need 60,000 amps, you put 5 of those, 2 or 3 of those lines, you're in business. Then the question is, what you need, therefore the voltage will be lower, and now it can be either cold or warm solid material, and that will be chosen. Or perhaps also the cooling medium itself could be the insulator. For instance, liquid hydrogen can be a practical insulator for this kind of voltage. Also, compressed helium can be an insulator itself. So there can be either the gas itself or can be an extra insulator to be added. Now, of course, the important question of this business is safety. Recovery procedure, worst conceivable accidents. And then also the other question, of course, which has to be included is redundancy. A number of solutions with either partial or total duplication of critical component is necessary. In our case, we're taking full duplication of the system. Now, I will briefly spend a few minutes of my time to give you two indicative solutions, which are the ones which are going to be the baseline for the future discussion work which we are going to have in the future. The first alternative is hydrogen. Now, you can see here the drawing of the system. It's a tube in which you see two of these cables of 20,000 amps, which have already been operated at CERN. Put one in there, the other one there. One is positive, the other is negative. This gives you a dipole signal. The inner tube has a single-phase hydrogen, which operates at 16 Kelvin. And then the return tube is also a hydrogen going the other way around. So, in fact, what happens is that the insulation between here and here is between 16 degrees and some very low voltage temperature, which is somewhere between 17 and 28 degrees Kelvin, which is the traversal of the tube along the return path. So with a double path, one inner tube inside and a return tube outside, that you can obtain a situation in which essentially the inner tube is operating in a very constant temperature, can travel for a long distance because he has another return tube which works as a buffer. And then out there you put in there a super insulation with 60 layers of MSI, and that gives you the 300 Kelvin insulation from outside. So this is fundamentally a very, very simple system which can provide you the dual solution as a possible alternative. The inner cable carrying the tube is remarkably thermally stable since it's entirely protected by the outer tube with a only slightly higher temperature. Now, this is how it looks like. You can see here, you have here the situation. This assumption, we assume to have 300 kilometers between cryocoolers. You can see here that we have a cable going down here and returning back in return. So the cryocooler goes in 150 kilometers back and forth. The inner part is here, and then the outer part comes out. The same is repeating itself here. Like here is the hydraulic plug between the system. A superconducting line may require a hydraulic plug here to separate from one unit to the next. But every 300 kilometers, you have such a system. And so forth and so on, with cryocooler here every this kilometer. The data here are clearly indicated. You can see the initial, sorry, Jesus Christ. You can see, this is a terrible system here. You can see here that the initial pressure is 20 bar in this particular model, and the initial temperature is 17 degrees going 17 degrees. Inner tube is this diameter indicated there. And essentially, the cryogenic power is rather modest because it's about 600 watts per kilometer used by this such a system. Then it goes to the other part, which is the outer system, which is you start from 17, you go to 17 bars, and then at the end of 150 kilometers, you lose some pressure. You get only 10 bars in here. The temperature goes from 16 degrees to 28 degrees. This is a return tube, and the travel time is so many hours, and so forth and so on. And the vertical depth for a 5 bars change is almost 500 or 800 meters of height. And this is the kind of structure you're dealing with. You can see here that probably what you like to have a fully duplicated system. So this is fully duplicated in our calculation, in our consumptions, because for redundancy, so you have two systems. One of them it'd be enough to take the full power. Presumably you're going to have both of them running in order to maintain safety, like in nuclear reactor, by safety and that. The simplified refrigeration scheme is shown here. This is a refrigeration system. There are two liquefiers in this description. One at 7, which goes from 300 degrees to 7 degrees, the first compressor here, with a Thomson valve in here. Then you get a second compressor between 70 degrees and 15 Kelvin, another Thomson device. Then you produce a reservoir for liquid hydrogen here. And the hydrogen goes and back and forth in both directions, 150 kilometers one way, 150 kilometers the other way. There is a heat exchanger here to recover the heat, and it pressurizes the system. Of course, there is no hydrogen is available except the hydrogen reservoirs for capacities, and each station you have this station represented here. The main parameters is, of course, between the inner and cryogenic is very modest. Only a few layers of simple separation amongst the two surfaces is sufficient. The mechanical pump has a certain efficiency coming from cryogenic phenomenon, going from 15 Kelvin to 300 Kelvin
the effect of the heat dissipation is thermodynamical efficiency is calculated there. You assume that there is this is 35% of the Carnot cycle, and those are the values indicated there for this formula. Therefore, about 50 times more power is required from the mains than what you really use in order to do the cooling. So it's not very bad. During normal operation, the cryogenic flow is closed and no hydrogen is lost for the environment. A considerable amount of liquid hydrogen is required for the initial filling. This is an important question, about 100 hours and 300 kilometer distance. The transfer of the accumulated amount of liquid hydrogen is something like 1,000 tons. 1,000 tons of liquid hydrogen is not an impossible thing for space, but it's a substantial amount of gas. The bulk cost of liquid hydrogen is only $2.50 per kilogram, so therefore the cost of these things is relatively very, very modest, but it's quite a substantial system. And I would like to underline that the safety requirement of such a large amount of potentially flammable cryogen must not be underestimated. This is the main question behind this. It's very elegant, very simple, but it requires to live with 1,000 tons of liquid hydrogen in a tubing system, and so forth and so on. The second alternative is dual helium gas liquid nitrogen line, which is represented here. Now, it starts with initial pressure 30 bar, at running in 15 Kelvin. And this is the part with helium gas. You have the same system here, helium gas. And that is surrounded around by a nitrogen system, which works between the temperature nitrogen system, between that and the room outside. So it's a dual system, nitrogen input, nitrogen return, hydrogen, helium input, and helium out. Helium is gas in this particular case. Now, the input temperature of the liquid nitrogen is 65 Kelvin, and the pressure is 30 bar. The diameter of the system is slightly larger. It's about 50 centimeter diameter rather than the 30 centimeter of the previous system. It's more complicated, but it has the advantage there is no flammable material in here in this particular system. The general parameters are shown here. I will leave them to you for your attention. Essentially, the key element is, you can see, represented by those numbers. And essentially, it's all quite understandable. The real question of helium is important. How much helium do you need? And comparing it to alternative. The helium temperature is somewhat arbitrarily chosen at 50 Kelvin, although even a slightly lower value may be chosen. The mass flow of helium in this particular system is 100 grams per second, corresponding essentially to 3.9 cubic meters per hour of gas at 30 bar. Each of the 4 units, the 4 central part. The helium needed for each 230 kilometers is 288 tons. About twice the present stockpile of the LHC. So it gives you a measure of what you do. It's roughly 300 kilometer system will require the same amount of helium. It can be improved a little bit probably by optimization, but that's the order of magnitude. The estimated cost of liquid helium is $18 per kilogram, so it's perfectly acceptable. The other question is also the production worldwide of helium is another important question. It's 30,000 tons per year, 10 times 3,000 kilometers line. So every year you could make 30,000 kilometers of tube with the helium you have available today if you have no extra additional helium generated by activity. So the amount of helium around is perfectly sensible, perfectly acceptable for the program, although it is significant. Okay, now, let me also give you one number here, which is important, and if we get into the end. So summarizing, a 300 distance of 300 kilometers of duplicated tube with a Carnot factor 55, with all power indicator there, will require a total amount in the hydrogen 21 megawatts. 21 megawatts will be the power required, generated by the system, AC to the supply system. If you were to go to the helium nitrogen system, the helium is much smaller, it's 1.64 megawatts of power, but then you need 6.2 from nitrogen in here, which is there, and these are the numbers, of course, meter cube per hour, 37, 3.8, 29. You see that liquid hydrogen or liquid nitrogen are quite similar in quantities, and the liquid helium is, of course, buffering the system, saving the problem of introducing the hydrogen. The Carnot cycle is 9 for the liquid nitrogen temperature, 55 for the helium part. Okay, now, the refrigeration scheme is a little bit more complicated, as you can see here. We start with an environment in which we run at 300 Kelvin. We have first compressor going to 70 Kelvin.
And we have a heat exchanger, a compressor 2, which is working on this. That 70 Kelvin is used to run the liquid nitrogen. You can see here liquid nitrogen is running at 65, 70 Kelvin. And goes into liquid nitrogen tubing here and there. It returns from liquid nitrogen tubing, so go in there, it returns. And then you get a second liquefier between 70 Kelvin and 15 Kelvin, which is much smaller, which runs with its own Thomson valve and is used to produce helium gas, which is used by the system, with a pressurized helium tank in there. And this is the kind of system that you need every 300 kilometers to do that kind of system. Okay, now let me also now come to the conclusion, another few minutes. Let me tell you here the big fundamental difference between the various alternatives. Here is the top line is the aerial. This is 5 gigawatts with various cables. I mean, we'll learn more from our people. The simplest and the smallest system is the 125 kilowatt DC superconducting cable, which is much smaller in size and is much less demanding than underground cable, and in particular all these other units. The other important question here, cost. You can see that the cost of the system is the highest for a cable, underground ordinary cable. It's second for high voltage DC. And thirdly, down here comes from this solution on our superconducting cable in the system. Let me also remind you something about the visual impact. This is the visual impact of a 5 gigawatt aerial. It's quite a bit of a system. Here is a situation of the tube, which is the tube which is represented here. This tube is actually a natural gas tube, and the actual superconducting tube is probably a factor 2 to 3 smaller in diameter. So it's a very modest tube which can do the job instead of having this huge analysis system which is there. Now, summarizing, therefore, let me continue here. We summarize with these conclusions. In general, the concern related to overhead transmission lines are connected to one of several following issues, which is visual impact, alteration of natural landscape, possible impact on health, environmental impact, economic impact on benefit, projection of common interest. You can see here a picture which comes out from a German demonstration story, which he says up there you can read, bury power lines, not children. And you can see the picture of these people complaining about building in overhead power lines in Germany itself. This gives you the taste of what you're going to get if you continue that line. Superconducting transmission lines have several advantages relative to public acceptance, smaller size, considerably reduced land use, practically none of them, no electrical losses, and lower costs are possible. Now, an important relationship which is still worthwhile, this is my last statement here, is comparing our system with natural gas pipelines. The rasterization of superconducting DC line has several elements in common with the established practice of natural gas pipelines. In the case of natural gas pipeline, this problem has been solved, and they're expected also to be solved also per superconducting DC lines. An elevation change of 100 meters will increase the pressure of the natural gas line by 2 bars, the one of liquid hydrogen by 0.7 bars, and the one of liquid nitrogen by 9 bars. So these are the numbers which are comparable. So you can see that the liquid hydrogen will have a much more less sensitive effect to the altitude, 0.7 bar for 100 meters, to be compared with the 2 bars which you have in natural gas line, because of the mass gas line, and 9 bars which coming from our solution with liquid nitrogen. So the choice is between the 2 numbers. The April report, for instance, described 2 parallel neutral gas lines, each carrying 500 million cubic feet per day, corresponding slightly to 6 gigawatts, with a compressed electric consumption of 100 kilowatts per kilometer. And this is a line which you can carry per every kilometer, essentially 6 gigawatt thermal. And it has to be compared with the number which I already gave you, which is 77 kilowatts per kilometer, a 25 kilowatts per kilometer of a 10 gigawatt electric line for hydrogen or helium plus nitrogen. So you can see that also the amount of consumption for the gas is in fact manageable. You can see here that in fact sorry, this is terrible machinery here, sorry. You can see here that in fact you can see that the 100 kilowatts per kilometer of 6 gigawatt thermal compared to 75 or 27 kilowatts per kilometer of electricity. Remember, there's a factor difference in electricity there. The CC line compared to DC with the AC compared to natural gas is, of course, a factor 2 smaller in diameter, at least a factor 2 to 3. The typical diameter
of this line here is 1 meter. And here we are talking about between 30 and 50 centimeters. And high voltage of the order 100 kilovolts, which is much lower than many of the demands of the power lines, and which of course can be corrected. And a small factor 3 pressures. We are running at most between 20 and 30 atmospheres, while the pressure of the natural gas pipeline is 100 atmospheres. And then, of course, the problem is cryogenic, which is not there for the normal natural gas, but should be there, and a good vacuum insulation, which also is required for, okay. So the bad things, a good vacuum insulation and a cryogenic temperature, which require proper steel. The good factor is factor 2 smaller diameter and a factor 3 smaller pressures and a high voltage, which is relatively modest. Okay, now let me continue with this. Now let me show you here, just to give you an idea, which is one of my last transparencies, the natural gas line in the European Union. This is the present situation of major power lines. Those are big ones. And you can see that they have been already covering quite a bit of land, and therefore if we're adding to this line some few tubes carrying electricity, with it will not be, since the thing will be relatively simple, we will be déjà vu, as you can say, so it will not be a major problem, this question. So therefore, the next step, which is ahead of us, is to be summarized. Original target of the program, namely the one demonstrating the feasibility of low-cost, reliable magnesium dipolarize cable transport reliably high current. Practical test has been essentially completed, that work which I gave you and can be discussed any further. In view of the success of the program and potential and aggressive future outlook, which what I would like to propose, should involve a firm commitment to, 1, the appropriate engineering design of the definitive cryogenic structure based either on gas, helium, nitrogen, or liquid hydrogen. The hydrogen solution is cheaper and simpler, but it requires a flammable liquid and somewhat higher power, but it's somewhat easier to compensate for latitude, altitude variation for the cable. For instance, if you want to go 1,000 meters underground, if you have a cable under the ocean or under the Mediterranean Sea, obviously the difference changes in density of the liquid will be an important issue. Oh, sorry, Jesus. Next question is practical extensive field test of tube length and cost appropriate. I mean, we need a practical extensive field test of tube length and cost appropriate to ensure industrial maturity. Provided such a design has been successful, the first industrial demonstrator of many kilometer length and power in a gigawatt range could then be actually constructed and operated. Let me summarize with a statement. The program may not proceed without major stopgaps, provided human resources and financial support are to be found. And I conclude with this. I have a little joke here. I'm starting to get concerned about global warming. Thank you very much. Okay. Finished.
Oui. Oh, ce truc, bon. Alors, je voudrais demander s'il y a des questions spécifiques sur l'exposé de Carlo Rubbia, et ensuite nous passerons à la table ronde et il y aura évidemment une discussion générale. Y a-t-il des questions spécifiques tout de suite Oui.
Ah, si.
Alors, micro.
Ah, j'ai une question, vas-y.
Ah, ok. Merci. Donc, c'est toujours Toufer Hasni. Je crois que Carlo me connaît bien et nous sommes bien avancés sur cette idée-là que je trouve absolument très intéressante si on veut réellement achever la transition énergétique. J'ai cependant quelques remarques à faire sur la comparaison entre l'encombrement des lignes énergétiques, entre le courant alternatif, vous avez parlé d'une largeur de 125 mètres, ce qui est exact, et pour comparer ensuite avec les alternatives, soit en courant continu ou bien en supraconductivité. Je voudrais juste vous faire remarquer que, en plus de l'encombrement, sur les transports énergétiques, il y a une bande de sécurité qui est définie par la loi. Autrement dit, ce n'est pas seulement l'encombrement physique qui détermine cette largeur de sécurité, mais c'est les risques liés au fluide transporté. Lorsqu'il s'agit d'un fluide d'un hydrocarbure qui a un risque d'explosion, la bande de sécurité, ça concerne entre autres les pipes de gaz. Donc, c'est un argument que vous pouvez ajouter pour dire que la comparaison entre le transport de gaz va utiliser une surface plus grande que l'encombrement physique lui-même, puisque vous avez la bande de sécurité de part et d'autre du pipe. Ce qui n'est pas le cas lorsque vous avez un transport par de l'hélium et de l'azote qui ne présentent aucun risque.
Je peux répondre de façon extrêmement simple. Nous avons deux choix possibles devant nous. D'abord, je voudrais dire que le travail qu'on a fait avec le groupe Columbus, avec les gens du CERN, etc., nous a démontré que la supraconductivité maintenant est sous contrôle. Donc les problèmes se déplacent. Ce n'est plus un problème de faire un câble, c'est un problème de faire la cryogénie et le système associé avec les câbles qui devient un problème. Gens différents, problèmes différents, questions différentes. Là, nous avons deux choix possibles. Une solution liquide flammable, qui est la plus simple. Combien d'hydrogène on est en train de parler? C'est à peu près 1% de la quantité d'énergie qui est transportée avec le gaz naturel. Alors, si nous transportons d'hydrogène avec une quantité qui est 2 ordres de grandeur plus petit que transporter la même quantité énergétique sous forme de gaz naturel, il est clair et évident que les problèmes sont là, mais sont substantiellement réduits par la difficulté associée avec le fait qu'il y a beaucoup moins de matériel. Par exemple, la vitesse de transport d'un tube qui transporte 4 gigawatts, 5 gigawatts depuis l'Algérie jusqu'au, disons, l'Europe est un diamètre à peu près 1 mètre comme dimension, une pression de 100 atmosphères, et il doit avoir des étapes tous les 100 km, 150 km pour refaire la compression. Nous avons un diamètre de 30 cm qui est un facteur 10 dans la surface du tuyau, et donc dans les poids du tuyau. Nous avons un facteur 3 dans la dimension de la compression, parce qu'à la place 20 à 30 atmosphères, c'est largement suffisant. Et donc, nous avons une vitesse la vitesse de mouvement est 10 mètres par seconde pour les gaz naturels et moins qu'un mètre par seconde dans notre cas. Donc, il y a tous ces facteurs qui nous disent qu'effectivement, c'est un problème correct, mais il y a la réalité qu'il y a des pipelines qui existent. Le monde est plein de pipelines. Tout pays du monde a des pipelines. Et ajouter une autre pipeline qui transporte de l'hydrogène à la place de transporter des gaz naturels, ce n'est pas tellement difficile parce que les risques sont similaires. Et donc, il est quelque chose qu'on peut gérer. Mais évidemment, il y a des préoccupations, des conditions, etc., etc. C'est la raison pour laquelle nous avons démontré l'autre solution, qui est la solution de faire du gaz naturel, de faire du gaz naturel qui existe à la place du gaz naturel, de faire un tuyau un peu plus grand, encore plus petit de l'autre, 50 cm, mais qui peut transporter de l'hélium gaz à 20 Kelvin, qui donc, ce n'est pas la même chose que les liquides, tous les problèmes de liquide disparaissent, et de liquide nitrogen pour refroidir, qui est quelque chose qui est largement disponible. Ce deuxième système, c'est un système un peu plus complexe pour ce qui concerne la construction, parce qu'il faut faire quelque chose de plus complexe, mais tout à fait faisable, parce qu'il n'y a rien de spécifique dans ce type de choses. Et ce système-là, c'est quelque chose dans lequel on élimine complètement les risques et tous les problèmes de sécurité, parce que le gaz hélium, il est tranquille, le nitrogène gaz, il est parfait. La seule solution que moi je considère comme préoccupante, c'est le fait qu'effectivement, si on va très profond, il y aura de grosses différences de pression, qui sont un facteur 4 ou 3, 4 plus grand que ce qu'on fait avec le gaz naturel. Alors le gaz naturel, on la voit sous terre, on voit le gaz naturel entre l'Algérie et l'Europe, sous l'eau, et donc on peut avoir une situation similaire avec ça, mais c'est un peu plus compliqué. Il n'est pas évident que nous ne pouvions pas faire un système hybride. On peut imaginer un système dans lequel on fait de l'hydrogène quelque part, et on fait, par exemple, loin, dans l'espace vide, et on fait dans les villes, on fait de l'hélium, parce que les deux systèmes sont interchangeables. Les matériaux étant les mêmes, les courants étant les mêmes, tu peux faire l'un que l'autre. Chaque 300 km, il peut changer. Aussi 300 km, c'est quelque chose de variable. Parce que moi, j'ai mis aussi 500 km, il devient un peu plus gros, c'est faisable. Bon, donc on a devant nous une option extrêmement intéressante. La question, c'est comment on va le faire, transformer ça dans quelque chose d'industriel. Et c'est ça la question sur laquelle nous devons lâcher.
Merci, Carlo. Alors, prochaine question, next question.
Okay. Thank you for the very exciting presentation. I have a few specific questions. One is that the current high voltage transmission lines that we have, they obey Ampere's law, which by effect it means that depending on the height from the power lines to where we are or where our building structures are, we have a magnetic effect, electric field effect, which is considered on issues of exposure. I wanted you to comment if Ampere's law and Messina or magnetic effect is there with the high voltage DC lines in this case. Number two is you have indicated that the resistance is very, very low, maybe close to zero with the process of superconductivity that happens here. But this is dependent on resistance, on the cooling temperature.
I don't understand what you say. Your words don't come through to me. Repeat what you say.
Okay, I have three specific questions. One is, could you comment whether this transmission has an effect on Ampere's law?
A defect?
Effect, yes.
On what?
Magnetic effect. Does it produce any magnetic effect?
A magnetic effect means if some...
When you transmit current from one point to the other.
What is the magnetic defect?
Magnetic effect.
Effect or defect?
Effect.
Magnetic effect. I don't understand what you're talking about. I'm sorry. I may be...
do you know Ampere's law?
Oh, sure, I know Ampere's law.
Yes.
You also know Ampere's law. We all know Ampere's law.
So
it's not under discussion.
Yes. So I want to know if this has any response to Ampere's law, number one, because if I am going to put my transmission 400 or 4,000 kilometers in my country, I wanted to know if that is there or not, number one. Number two is I wanted to know on the temperature. You have demonstrated 39K cooling. Can this be extended to room temperature, which is 273 or 300K? 273K.
230. Can you explain me what he says? I don't know.
Okay.
This works only at low temperature. It doesn't work at ordinary temperature. It works at 25K or something.
Yes.
Yes, but I'm reading here, supraconductivity tested has actually arrived to 168K, depending on other combinations. So I want to know why this is limited to this.
It's difficult to handle. And EGB2 can be made as wires, so that's an enormous difference, also in cost.
Okay.
The MG2, the so-called warm superconductor, is not a warm superconductor.
Okay.
Because it's operating a liquid nitrogen temperature.
Yes.
So they operate typically at 65 degrees Kelvin.
Okay.
Kelvin is minus 273 plus the number, so 70 Kelvin temperature, minus 200 degrees centigrade. So they are not warm, they are cold, but less cold than what we are doing at CERN. At CERN, we operate at 1.6 Kelvin temperature with superfluid, superconducting liquid helium. And here we are talking about 65, 70 degrees Kelvin from this so-called warm superconductor.
Okay.
The magnesium diboride is superconductor up to 39 degrees. So it is certainly a lower level of superconductivity temperature than the warm superconductor. But as we pointed out by our chairman here, it is easy to build in terms of wire, cheap to construct, because the material from warm superconductor are rare earths, are very complicated and expensive materials, which represents somewhere between a factor 100 to 1,000 more cost of the wires. And in fact, the availability of the material has been the major handicap of getting long lines carried with this system of warm superconductor. But magnesium diboride, as will be illustrated here by Mr. Grosso, which is the responsible person for the program, which will certainly tell you something, is magnesium diboride is something made by magnesium and boron. There's the world is full of boron, the world is full of magnesium. This is not a very sophisticated material. It's something anybody can buy and you can construct, and therefore you have availability of this material. The other advantage you have, this material, as pointed out by our chairman, can be made in wires. So in other words, he has already built a cable, which is 4 kilometers long, and he has promised to us that it's going to go to 20 kilometers length with one single wire. So one roll wire is every 20 kilometers you have to unroll it. This you cannot do with the warm superconductors, because those warm superconductors are very fragile, they can break and damage. So technologically, it's a fantastic improvement, and it will give you a lower temperature, but this is not so much lower than that will change the technology respect to what you do with warm superconductor, because between 65 and 30 degrees Kelvin is not a big difference. It's just changing your compressor. You buy the same compressor from the same company.
Yeah, Lastre, thank you. Lastre is modern communication using power or electricity. We have used power line communications, PLC, and also we are integrating fiber with communication. For example, in Africa. In the African continent, we have taken advantage of the power lines to also integrate communication.
Yeah. Yeah, YouTube probably.
We don't understand. What is the question now about superconductivity?
Yes, the question is whether these superconductive lines can support other communication, like optical communications, on the same line. Because you didn't work for Africa, for example, to replace with this high voltage and cut out the fiber connectivity, which we are also landing on the same.
No, but you know, because you're going to bury this small pipeline, you could, of course, in the same hole, put the fiber optics. But this is a different problem, and we'll hear about it later on. I suppose we must go on with the program. Thank you.
Thank you very much, Professor.